So let's start today's session. Um, so today I'll be talking about two things, talking about the triangulated structure on Motivic stable homotopy category, and then we'll move to seeing um the Eilenberg Maclane Motivic Eilenberg Maclane spectrum representing Motivic cohomology. So these are the main two topics for today. And yeah, let's just get started. So recall where we are at. So last time when I was giving a talk before Guano's talk, we defined this stable homotopy category. So what we are trying to do? So in normal topological cases, we have something spaces, that is your compactly generated weakly Hausdorff spaces, and out of which we invert the suspension functor to get your spectra, the stable homotopy category of spectra. And this is where the magic happens. Um, I don't think I mentioned in my talk introduction to spectra, but it is a triangulated category. I think I mentioned it, but I didn't really say how or how, or what or how, but it's really easy to see. Your suspension essentially work as a shift. So in this algebraic geometry world, whatever we're doing in this Motivic world, we introduced our spaces, but now the spaces are your Nishnevich sheaves, simplicial Nishnevich sheaves at yeah, simplicial Nishnevich sheaves basically. Um, um, yeah. Here, out of which we did two or three things. To be honest, we first we inverted your simplicial suspension to get your SHK spaces over. So this is denoted by SPCK. Your stable simplicial homotopy category. Then we want our A1 to be invertible, so we localize that A1 to get your SH A1SK. And then we want to get our Tate circle to be invertible as well. So for that, after doing that, we get your the Motivic stable homotopy category. And we are interested in this category in SHK. What you're trying to do as your actual spectra, your maps into the spectra in this SH category represent cohomology theories, right? So your SH, um, E is a spectra. This represents cohomology theory. What you're trying to build is something analogous for here. So we are trying to focus on this object in this setting, whatever that is. Before talking about that, let's talk about the uh, one of the big features of in this spectra. Everything is triangulated. Note that topological spaces are not triangulated, but simply because of this reason, because you can't take you can suspend up, but you can't suspend back. You don't get distinguished triangle, but spectra is triangulated, and your bispectras are also triangulated. So let's talk about that a little bit. So we start with we start with a spectra, a bispectra. And we want to find a triangulated structure over it. Okay, so we don't start with a object, we start with a map when you're talking about this triangulated structure. Start with this map E2 E prime F, and I can fit this in a triangle. For that, I have to take its homotopy push out. You will get something called as cone object. I'm denoted by CF, exactly how do we do it for topological spaces. And then point this E prime to a point. And you will get suspension with respect to your simplicial circle. And this is my shift. So this entire thing that you see over here gives you a distinguished triangle. And this is also your Motivic push-up. Yeah. Um, yeah. Yeah. So so this is how to get your distinguished triangle. Um, in particular, or I don't know, in general, if I have a distinguished triangle, this x, y, z, x comma 1. What do I mean here by this diagram? It simply means it's a co-fiber sequence. This is a co-fiber sequence. Or homotopy co-fiber sequence, to be more precise, homotopy co-fiber sequence in SPTSTK. Or co-fiber sequence in SHK. Doesn't matter. So if I have a sequence like this, I will get a long exact sequence of abelian groups. Yeah, before that it gives you a long exact sequence of abelian groups, it's important to note that um, that this guy x dot y dot, where x dot and y dot are spectra, any spectra, doesn't matter. This bispectra, simplicial spectra, your actual topological spectra doesn't matter. But both are spectra. It forms an abelian group. The reason is quite simple. Um, prove that um, this x, this x dot can be always written as, suspension square of suspension minus 2 of x. Now this will give you some element, I don't know, suspension square of x prime, I guess. Yeah. Now you can use your loop suspension adjunction to shift this suspension on that side. That give you suspension of x as a co-group object. This is the other side is a group object, right? And co-group object to group object, you have your Ekman-Hilton, and you can show that it's an abelian group. So it's an exercise. It's an abelian group. Yeah, this is one of the big feature of Spectra, that it by default comes with abelian group structure, co-group structure. So let's use that and get the long exact sequence of a abelian group. So you can apply this functor first, the covariant Hom functor in the stable homotopy category, to get this long exact sequence. To E comma yn, where this yn means, what do you think it means? It means shifts into x n plus 1, so on and so forth. And similarly, apply this contravariant functor to get a similar long exact sequence in the opposite direction. Long exact sequence, not writing the long exact sequence down. So already we have some resembling behavior, just like your Poupe sequences. So that's a good thing. The next is to keep talking about these distinguished triangles. So let's look at a lemma. Yeah, yeah, let's use a different page. The lemma tells you that if I have a monomorphism with respect to your pointed spaces in SPC, okay, okay, um, then I have a long exact sequence of your, sorry, you don't have, we do have a long exact sequence, then we get the following distinguished triangle. Get, which is not really hard to see, but technical, since we did not talk about the model structure here. So how to see this? So forget about everything, forget about this in the algebraic setting. For topological spaces at least, if I have a monomorphism of topological spaces x to y, and then I take this to the point and take the homotopy cofiber, not the cofiber, take the homotopy cofiber, I will get yeah, let's just write down, I will get the cone over this guy, so cone over your f. What is that thing? That thing is precisely your y over x, right? Because x is an inclusion. Are you guys following? I can't see any of your faces, but
Yeah,
uh,
we're good.
okay, good, good, good. So this is precisely this thing for topological spaces. And here we did not talk about the model structure, so I can't really talk about what the cofiber replacements are, but still, let's accept this for your pointed spaces here. And then you will get your this distinguished triangle because your suspension functor, this is yeah, so this suspension functor, it's it last time I did talk about this, I think so, I hope so, from here to your shk and back to back, this is your suspension infinity s comma t, and this is your evaluation map. This form a Quillen equivalence. And that means that this left-hand side, this suspension infinity st, this preserves homotopy colimits because it's left Quillen. And that means in particular it preserves the homotopy push out, and that's how you will get your required long exact sequence. Suspension infinity is comma t x y suspension infinity is comma t, and this is your suspension infinity is comma t I over x. So this is your homotopy push out. That means it's a cofiber. It fits in the cofiber sequence, homotopy cofiber sequence, and that's your distinguished triangle. From here you get the distinguished triangle. Cool. Uh, yeah. Let me see. Yeah. Then we introduce a tool. I think it's one of the signature feature talking about this Nishnevich schemes. But yeah, let's introduce that. Let's introduce that tool, and that tool is called upper distinguished triangle. So let's say we have this this etal map, between two schemes. V2x is P, this is your etal, and this is your, we have an open embedding of, I don't know, let me see which, they're choosing U, okay. U into X, this is your I, this is your open embedding, V2X is your etal, and take the pullback of this map, call it W. We say this is a upper distinguished triangle, is upper distinguished triangle. If we have this isomorphism of reduced schemes, P inverse X minus U to X minus U is isomorphism. Let's take an example, and your Zariski covers are examples of this upper distinguished triangle. So if you take X to be your U union P, W to be your U intersection V, then yeah, yeah, and that will give you your upper distinguished triangle. Um, yeah, and your Nishne in your Nishnevich topology, that has been discussed in the appendix. We have the generating. You have the generating covered for Nishnevich topology. We have the generating cover, which are of the form embedding. This is your Vital map. Yeah, and your P inverse of U. This is your W. This will fit into your upper distinguished triangle. So yeah, and what's special about them? So if you're talking about your representable spaces, these upper distinguished square are also, what I'm saying, triangle. These are upper distinguished, okay, square, not triangle. Never mind. Square, which is a pullback square, it turns out to be a push out square as well. That's the next level. And I think we proved this in our derived algebraic geometry course some time back, but just let me write it down. For representable spaces, oh, yeah, your upper distinguished square is also a push-out square. What does that mean? So that means that I can take any object, you know, um, from your smooth scheme and think of them, fitting in this upper distinguished square, which will also be uh, a push-out square. So that's that's the power. And using that, we'll prove the next two theorems. This push-out feature. So yeah, these are corollaries. Um, yeah, there is a distinguished triangle in SHK. We have, yeah, first let's prove the part one. So we have the yeah. So if we have a distinguished triangle U V W W U V, this is your X, then we have the following. distinguished triangle. Basically, you get the Meyer-Vittori sequence. These are all pointed. So let's add a point over here. So yeah, let me see. Give me 1 second. Let me see if I have done this correctly. Yeah, let's talk about it. So we have this square, right? Yeah, this is where I have hand waved. I did not understand it fully, but anyway. So this is your upper distinguished square. This is a pullback square. By the last discussion, last lemma here, we can conclude that this is a push out square. Now, apparently, this is not only a push out square. This is a homotopy push out square. I'm not really sure how or why, but let's just accept it. Now, if you accept this, then again, the same logic will apply here. It will give you a, or you apply suspension 20 ST. Your this suspension, I don't know what you how to call this functor, the suspension ST functor. This will preserve the homotopy colimit, so you will have this push-out square. Yeah, and then you have to play with the diagrams a little bit that show that this push out square is same as saying this wedge version, and then we'll get basically there from there we'll get the upper distinguished triangle. There is nothing much fancy going on. What might be surprising that why this push out square has to be a homotopy push out square. Again, I do not understand the model structure here, so I can't comment on that. But yeah, that's the crux here, this H part. So that's for your part A. For part B is something very easy, that there is a naturally induced stable equivalence between these two. So let me write down the theorem. So this guy, the suspension ST of U over W is stably equivalent to X over U. Now, this is very easy to see because this is not only a stable equivalence in terms of the spectra, these are on the space level actually homotopy equivalent. They're literally the same. How? Let's go back to our push out square. W V U your X now. So this is your push out square. Um yeah. I think it's okay. Let me write this down first. So X will be your U union W V, right? And X mod U will be your U union W V modulo U. Now that means that yeah, you are squeezing, you are identifying W U with a point that is same as saying you identify the V part, W part in V with a point. So these two are equivalent on the space level. So on the spectrum level, they will give you your um, stable mode of equivalences. All right, let me take a break. The next part is to introduce you the state sphere. Yeah. So, yeah. Um, we have two suspensions here. So this is about it. Now, next idea is to introduce the date sphere. So far, we have talked about two circles, your simplicial circle and your Tate circle, right? If you take suspension, if you take, so if you take suspension of your simplicial circle, you will get two-dimensional simplicial circle. If you get suspension of your Tate circle with respect to your, obviously with respect to your Tate circle, you get the two-dimensional Tate circle. The idea behind Tate sphere, sorry, two-dimensional sphere, yeah. The idea behind Tate sphere is that you suspend the simplicial circle with the Tate circle. What is this object? And this is exactly what we are going to identify. We will show that this is the part A in stable Motivic stable homotopy category. The suspension spectrum of affine line quotiented out by your Tate circle gives you this guy. Yeah. Why is this true? Let's talk about it. So, so note that we have the following homotopy co-fiber sequence. A1 minus a point included in A1. And then you take its co-fiber, homotopy co-fiber, you'll get something like A1, yeah, A1 over A1 minus 0. Now, yeah, yeah. From here you get the long exact, you get the distinguished triangle with in the SHK. So your distinguished triangle will be the suspension infinity ST. A1 minus 0, which is your Tate sphere, by the way. Yeah. Now, what is this thing? This thing is actually fitting into a homotopy co-fiber sequence. That means it's a push out of this diagram. Let's just shift them a little bit. It's a homotopy push out of this diagram. Now, homotopy push out of this diagram is same as, so this is where contractibility of A1 hits in. I think this is the first time we are seeing this A1 contractibility playing some useful role. Now this A1 is contractible. What does that mean? This means that this is a up to homotopy. This is same as saying boom, boom. Now what is the homotopy push out of this guy? Well, it taking the suspension with respect to your simplicial circle. This is your suspension on S of suspension infinity S comma T, A1 minus 0, but A1 minus 0 is your Tate circle. Let's use that notation. And S1S is your suspension S, infinity comma ST, S1T. And the by default definition of the spectra, you can show that you can just take this thing inside. You don't change a thing. So for how should you think about it? Forget about this bispectrum thing. Think about your normal spectra. So from a topological space X, if you from a topological space X, nothing, no bispectra is involved, just as normal space. You can always build a spectrum, your suspension spectrum, or you can think of, applying the suspension, yeah, and then take it and then suspend it. So suspension, let's use the smash notation. Yeah, that's why I don't like the suspension infinity symbol. I don't think there is no infinity involved here. I think the correct symbol should be like suspension dot. Yeah, but anyway, and then let's just suspend it. Suspension infinity x, and then here if you just take your normal suspension and then apply your suspension infinity function, you're ending up with the same thing. So similar thing is happening here. It's a bispectra, but you are only playing with the simplicial part, so the logic remain more or less the same, and you will get your desired result. So that's one way of viewing Tate circle, like A1 over A1 minus 0. There is another way, or there is another identification going on. The other identification is the following. So this is your part A. Part B is the theorem is that um, for the projective space, suspension spectrum of the projective space is same as suspension spectrum of the Tate circle. Sorry, Tate sphere, never mind. Tate sphere. How to do this? For this, we will use the Meyer-Vittori sequence in this case. So note that this P1 is nothing but your union of two affine lines. Yeah, let me write down the push out square. Boom, A1. Okay. And now we can, now given this push out square, so this is also homotopy push out square because these are inclusions. So this is, I think, is easy to see. And after which you can apply your, this suspension spectrum functor and use your Meyer-Vittori sequence. So basically use this lemma to get the to get this thing out of it. So basically use this corollary. I don't know, let's call this star. You start to get zero to A1 suspension A1 this is your P1 and then there is some shift, not writing that down. Okay, now yeah, over here there is some technicalities going on. I will ignore all those technicality apparently. So what you do get actually is not just a spectrum. You get with respect to your pointed spectrum, like so you have to from spaces you have to land in your pointed spaces, then out of which you get the spectrum, right? What they are saying is that in the notation that choice of the base point won't matter, and they're showing that you can always choose this base point to be your 1 in this case. And modulo all those technicalities aside, you can always contract this guy. That will land up in the exact long exact sequence that we were talking about in the, sorry, not the long exact sequence, the distinguished triangle that we were talking about previously. That is the same as this one S, same as this one T, but the previous discussion, and this two will coincide. So this is another way of viewing the state sphere. So let me define the state sphere now. Your state sphere is defined to be T state sphere. You want to find line as puncture fine. Okay. Um, yeah. Next, let's briefly mention your Thom spaces, because yeah, to talk about the Thom spaces, we need to. I mean, I don't know about but I personally need to develop some more tools to talk about this homotopy purity theorem. And right now I'm not ready, so I just briefly mention Thom spaces, and then we'll move to your Motivic cohomology theories. So yeah. That's the plan. So before I do that, let's see if you have any questions or not. Okay, so let's move to Thom spaces. So how do we associate Thom spaces or Thom spectra? We associate the Thom spaces for a vector bundle, right? So we basically take the 1-point compactification of the vector bundle to land in your Thom spaces, of the total space to land in the Thom spaces in your topological spaces. But here is this analogous version for this your smooth schemes, and you literally associate the Thom spaces in the analogous way. So if you have a vector bundle in your smooth schemes over K, your vector bundle, um, then let's specify a zero section. I such that x2 zero section. Then your Thom space of your vector bundle E, fancy E over X, is the following. And you can show that for a trivial bundle, yeah, for trivial bundle, your Thom space is in suspension with respect to the Tate sphere. This is your A. There's another property that, yeah, it respects this analogous version of product structure of vector bundles that we encounter in Thom spaces. So if I have two vector bundles, then satisfies this relation. Yeah, when you talk about the thumb spaces, it's really the things that you want to talk about is your thumb spectra, the mu spectra, stuff like that. But I have not encountered those stuff like in these notes at least, and the algebra, the smooth scheme version. So yeah, let's just go ahead. And there is this homotopy purity theorem that I would only mention. Suppose we have a closed embedding z to x to I, and yeah, and let's talk about the normal vector bundle with respect to this closed embedding. Mm. Z of z, yeah, normal z. Then we have the canonical isomorphism. X modulo x minus c. And then in the notes, they go on talking about proving this theorem and talks about the transfer map, but I will not talk about it. Yeah, the last thing I do want to talk about today is your Motivic, Motivic Eilenberg Maclane spectrum and Motivic cohomology, and it will be done. So, yeah, let's talk about your Motivic Eilenberg Maclane spectrum. So let's recall how we usually defined our Eilenberg-Maclaurin spectra associated to your um, you know, Eilenberg-Maclaurin spaces for topological case. So I can always associate a Z uh, or a G depending on which group you're taking. So spectra such that at the nth level space your KZN, and it gives you a loop spectra, or sorry, not loop spectra, omega spectra, and yeah, and it's cohomology, and it represents your actual singular cohomology theory. So what do I mean by that? That's the important part, because this is exactly what we're trying to imitate. So this is your usual singular cohomology theory, nothing special, nothing fancy, like for actual topological spaces. That is same as in the stable homotopy category of spectra, the maps out of this suspension spectra H Z. Okay, I'm in a tricky situation now. Hmm. So just call this dot, I guess. Yeah, I hope that does the job. So Can somebody confirm this is true? Like whatever I wrote down here.
Yeah, usually I think of this in the unstable version, where the nth cohomology is the map of X into the nth Eilenberg Maclane space.
I know, but I really want something like this because then I want to talk about your
So
SHQ.
the thing on the left is a graded abelian group. Is that the point?
Yes, 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 yes. And on this is your graded abelian group, and this should be also your graded abelian group. This is abelian group, I can see that much. And I think the fact that it's graded also comes from, yeah, yeah,
Yeah, it looks like it should be right.
yeah. Anyways, or something similar to it. Let's just believe it. Let's just box it up. So here is the thing. Yeah, we are trying to imitate this in our Motivic stable homotopy version. So yeah, that's what the next part of the talk goes on. So in our Motivic homotopy, we are trying to create this HZ spectrum. It turns out that it is impossible to construct a bispectrum that that gives you something like this. It does not represent your singular cohomology theory. However, you present, I think they are using a similar notation, but this H is more bold now, that it represents Motivic cohomology. And that's one of the big points of Model and Borovsky. So let's talk about it for a while. So you start with your smooth scheme. And given a smooth scheme X, I am associating a functor Lx, associate Lx. How does it behave? It takes an element scheme over K and associate. So this is a long association. Let me write this down. It's a free abelian group generated by closed irreducible subsets of which are finite over U and surjective over the connected component of U. I have no idea why this is the definition, why we're restricting ourselves to this particular subsets of U cross X, but this is the free abelian group that you are trying to associate to.
Can I
And
jump in here?
yeah, go ahead.
This is a manifestation of a theorem of Doldin-Pupa,
Okay,
which constructs the homology of a space in terms of an infinite symmetric product.
okay.
Yeah, you see, this is one of the founding. If you look in this article of Friedlander, I think it was Friedlander's article, where he explains these ideas of Suslin and Blavatsky. A starting point for the whole theory was that this is a theorem of Dold and Pupa. It says that I can compute the homology groups of any space from the infinite symmetric, from the homotopy, basically, of the infinite symmetric product of the space. Okay. So
Okay.
I'll just leave it at that. I mean, of course, it looks totally unmotivated what you're writing down here, but this is really one of the founding observations of the whole theory. So it's practically on the first page of this article of Friedlander that I
Okay.
sent you.
Okay. Thank you so much, Hoffman, for rescuing me. So apparently, even though it looks dry, it has some historical motivation to it. I will just put it that way. And in
Yeah,
this
I'll maybe also add something. Like, so I think
okay.
we skipped this section, but like these are correspondences, right? Um, so you have like some or some like it's a free billion group on correspondences with some tweaks or whatever. And uh, like one strategy of studying um like when we did this initial version of motivic spaces that Guan Yu described, uh, we kind of left this open thing of like, how do you actually construct from this the like motivic Eilenberg Maclane spectrum or like setting the stable stuff in general. And doing this, I mean, there's obviously we have this approach that we did in the last couple of weeks, but you can also do this approach where you look at correspondences of smooth schemes, and you can build up a theory that way that kind of like models the stable category. And you can use this to do this Eilenberg Maclane stuff as well in that way. So I think section. Let me find the section really quick, but
Okay. Okay. So I
yeah,
see.
and in the notes in uh, part uh, 4, uh, chapter 2, section 3, they have some good stuff on this.
Okay. Okay. Yeah, I will take the reference from you later on, but okay, thank you. Thank you for mentioning this. Okay. Anyway, let's move on. So this free aberrant group that you associated to each smooth scheme. And elements of this group are called referred as cycles in these nodes. And here's the fun part. Your Lx not only uh, is just it not only just a functor, it turns out to be a Nishnevich sheaf. So it's landing in your abelian groups, but it's if you just forget your just the group structure, it's landing in your sets, and that's why it's a pointed space. So yeah, this is how you can view that as an element in your pointed space, pointed Motivic spaces. So this functor this is the functor that we are trying to focus on. This functor, this L functor. You can upgrade this functor from pointed spaces to um yeah Nishnevich sheaves with values in simplicial abelian groups. So this is why they are giving an example L of S1, the Tate circle. This one says is Tate sphere. This is same as your L of A1 minus 0, comma 1. Now this is same as saying your L of A1 minus 0, sorry, A1, no, I wrote this correctly, over L of spec K, and yeah, and this equivalent you can write down. I don't know exactly how, but I will just write the facts down here. So equivalent to E, this is your same as yeah. If you want to chime in and help me out, I'll be happy. But otherwise, I'll just keep writing. And if you evaluate this guy at C, you will get your CP infinity or your KZ2 back. So you are getting your second Eilenberg Maclane space back. So that's a good thing. That means that you need to focus on looking at, oh, I think I messed up. Is it S0, not S1? We need to focus on these objects. In this particular case, it gives you your KZ2 back. So that means that I should not say this means that, but it gives you some kind of motivation that let's focus on these objects. That's all. Focus on here. Note that we have a yeah, we have a induced such a smash product here. SP is T L of SP is T to SP is T. Using these, we can define your the connecting map, the structure maps. If we take these to be our spaces, this L to be our spaces, basically HZ F comma N is defined to be L of your SMS plus T. There you go. This is your Motivic Eilenberg Maclane spectra. You must be wondering where the structure maps are coming from. Structure maps are coming from here. This will give you structure maps. And in the paper, they show that your Motivic cohomology can be computed from here. Yeah, this is why I was tripping beforehand. Over there, this is your E comma skew smash skew T smash C. This is your Motivic cohomology. So modulo some suspension with respect to these two circles, it represents your Motivic cohomology. Yeah. And yeah, that's I think a good place to stop.